This is the video solution for the Dynamics Exam 1, Spring 16. Well, this first problem was just to see if we could do a little equation manipulation and try to come up with some answers given in all cases here when t is equal to 5.29 seconds and s is equal to 30 meters, we wanted to find out the velocity. So in this one, all you had to do is just plug 5.29 into that equation, and then you get there. This one, we needed to do a ds is equal to v dv, and recognize we have to integrate that. Many people did okay on that. A lot of people messed up this integration on this side, unfortunately. So integration of v dv is 1/2 v squared. So that hurt a couple people there. This one, I had to recognize v is equal to ds dt and take the derivative in order to find out what the velocity is. All right, and then this next one is just the pulley problems. Those were fairly straightforward if we remembered how to calculate the pulley ratios. And so this one, if you do a little, draw the P's. This is the easiest way, I believe, is to follow the P's. So if that's force P, that one's P, that's P, that's P, which makes that P there, and that one 2P. Or you can draw the little section right there so you know that that's a 3-to-1 ratio. This one was well, follow the P's. So we got P on both sides there, makes that a 2P. Follow that around, so that's 2P, 2P, and 4P, and you can see that that's a 4-to-1 ratio, and by the same token you get this one is equal to a 4-to-1 ratio. Couldn't give a lot of partial credit on this first page because they were just 2 or 3 points apiece, and you almost got them right or got them wrong. It wasn't a lot of work to show, unfortunately. Okay, this next one was just the area under the graph technique. So we did this one, pretty much this exact one in class. I gave you a few homework problems as well that looked very similar to this. But anyway, what we're looking for is the area under the acceleration graph is the change in velocity. The area under the velocity graph is the change in position. Didn't ask you to actually draw the ST graph, but I wanted you to use at least the area under each of these guys to come up with the total change in position as we go forward. So in other words, so we have for 5 seconds it's accelerating at 2, so the area under there is 10, so you know that it accelerates from 0 to 10, so that's going to be the first point. Area under that is 5, so we have additional 5 change in velocity, so from 10 to 15. So those are going to be the 2 points, and then here the acceleration is 0, so we know that it continues on at a constant speed. Looking at the area under the velocity graph, 1/2 BH here is 25, that one's 50, this is 150, and then that is 12.5. You add all those things up, and you get the change in position is 237.5. And again, you didn't need to, we weren't required to draw this graph, but if you did, then it needed to be done correctly. But we want to line up these times, right, like that, so that the position here is 25, which adds up to that area. The change in position from here to here is whatever that is. So that from 25, then it needs to add up another 62.5 to go from 25 to 87.5 here. Then add another 150 to go from there to there. This one, the relative velocity pictures here, we did quite a few of these in class, as well as we had a quiz on this, so I was hoping that you'd be pretty prepared for this one. But again, we want to find out the actual versus the relative. And if the student's going to throw the rock from the car and hit the sign, we know that this is the actual direction of the rock. The actual direction of the car is straight up, so that was pretty simple. The relative one is where he has to aim it and how fast he needs to throw it, and that's kind of what we were looking for. I gave you this angle, I believe, yes, the angle is 10 degrees right here, but I didn't give you how fast he needed to throw it. And so that's what our whole question was, is how fast does he need to throw it in order to hit the sign at B. So if we set our definitions of the 3 components up into the equations like this, or into the form like this, we got VI is 35J. The velocity of the rock is an unknown magnitude, but we do know the direction by just doing a little bit of trigonometry, we can find that direction is cosine alpha sine alpha, and alpha being 38.7 degrees. The velocity of the rock with respect to the car, the relative term, again, we have an unknown magnitude, an unknown speed of the throw, but we do know the direction because that was given to you. That angle of 10, cosine 10, sine 10. Putting those into the one equation, then we just put that like that, separate the i's and j's, solve for the actually two unknowns here. You only had to really solve for one, but I did solve for both of them here. If you do a substitution here, velocity of the rock, and plug it into the second equation, then you can solve for the velocity of the rock with respect to the car straight into there. And again, many people thought that this was the speed of the throw, the velocity of the rock, but it was important to know the difference between the actual and the relative. And so if you put this as your answer, I had to take off some points. If you circled them both, I had to know which was the speed of the throw, so I took off a little bit if you circled them both as well. Well, this next one was a car going over a hill, and when you go over a hill, your normal force goes down a little bit. We call that whoop-de-doo in class. Anyways, the way we start this is we recognize you have to draw a free body diagram. Free body diagram is how we get started. So let's draw the free body diagram here. It's going in this direction, so I have a tangential direction there, a normal direction pointing in toward the center of the rotation in there. The angle theta is the angle that the normal makes with the vertical, which is also the same as the angle the tangent makes with the horizontal. Either way works, but you have to put an angle on the drawing. If you're going to do sines and cosines of an angle, you have to tell me what angle you're talking about. So I did take off, if you did not label the angle, that's an important part of the free body diagram. We have a normal force, we have a force of friction, we have an mg sine theta, mg cosine theta. Those are the components of the forces on the free body diagram I was looking for. Then to get started with the actual calculations, we take the derivatives. So we have an equation for this line or this shape here, and we take the derivative once, take a derivative twice, and recognize that the angle is the slope, which is the value of the first derivative of dy dx, and that's inverse tan of 0.125, and you get the slope, or the angle there is 7.125 degrees. Plugging our derivatives into the row equation, we get that 163.7 meters. And then to find the normal force, which was our first question, I guess I should just leave that right there. To find the normal force, we plug it into the sum of the forces, normals, mass times acceleration, normal. And here again, many people mess this up. In fact, most of you mess this up, unfortunately. But the sign, the SIGN of the normal, positive normal direction is pointing in. That means that mg cosine is a positive value, and n, the big N of the normal force, is actually negative. So then when you sum the forces in the positive direction, we got negative normal plus mg cosine theta is equal to mv squared over rho. And plug in those numbers in there and you get 14.58 kilonewtons. All right, the next question was, he now slams on the brakes, he skids the tires, coefficient of friction between the tires and the road is 0.5. We want to find the deceleration of the car. Well, let's go back to the free body diagram. If he slams on the brakes, then it is a skidding or slipping condition, as such that the force of friction now is equal to mu, force of friction up here is mu normal. So plugging that into our sum of the forces in the tangent direction, we get this, we get plus mg sine theta down the hill minus force of friction going back up the hill is equal to ma tangent. Again, knowing that force of friction is mu normal, plugging those in, you get the tangential acceleration of 2.4. Now this box problem also stumped a lot of you, unfortunately, but here it's a fairly straightforward. Some of the forces in the x is mass times acceleration in the x to get the system. And the system travels together. That's what we wanted to communicate, and the stuff that we did in preparation for this is that when you pull on this cord here with a force of 400 pounds, those two boxes travel together as a system. You have to find the normal forces here in order to find up the friction forces. So that's what I did first. Some of the forces in the y, and as it turns out, it's kind of interesting, and most of you caught this, but some of the forces in the y over here is the sign component here says that the normal force at A is equal to 0, so it has no friction on that portion of it. However, you do have normal force over here, so you get a force of friction of 150 pounds here. But then, again, in order to find out what that tension is, what we're looking for is the tension in this chord. You can't do that without finding the acceleration. You do that by either doing two free body diagrams and solving them separately as a series of I guess there would be a two equations, two unknowns kind of problem if you solve them separately, or you can solve them as a system and find out the acceleration of the system. And so that's what I did here, is that I sum the forces in the x as mass times acceleration in x. I only have that F cosine pulling it, only have one friction force, but when you do it as a system, you have to include both masses, and so that you find the acceleration is 12.65. Now that you know the acceleration, now you can find that internal force, that tension, by doing another sum of the forces equation, where I have that tension pulling here, I have the force of friction pulling back, and I can find out what that tension is with that one equation. Then the last one is our banked track, or our we did this one in class actually with just different numbers. I gave you, I think, 3 homework problems on banked track, so I was hoping that we'd be prepared for this. But what you do is you recognize here that the normal direction, this is an NTB problem, this is the normal direction points in from the object to the center of rotation, and it's rotating straight in like this, or here's the center of rotation in here someplace. So here's the normal direction, the B direction is vertical, and the tangent direction comes in and out of the page. So there is no acceleration in the tangent direction, only in the B and the normal direction. Well, actually, there's no acceleration in the B direction either, because that would mean it would be slipping and leaving the path. So what we've got is set the free body diagram up properly. You got normal, B. You know that there's a normal force, a big N, which is perpendicular to the slope or the road, and then we got an mg coming straight down. With that, then find out those components in each of the normal and B directions, and then we just sum the forces in the B is 0. And we do that, and we can find out the normal force of 76.69. When you sum the forces in the normal, we have to recognize that sum of the forces normal is mass times acceleration in the normal, and then you can find that the Vmax is Vmax is equal to 78.95.